All right, CNT140, we are looking at Chapter 8 on fiber optic testing. So if we look at the objective of the chapter, we're looking at parameters to be tested, instruments, meters to use, how to use those, uncertainty, troubleshooting, that sort of thing. And just a little heads up on this chapter, we have a number of the meters and tools that are talked about in this chapter. So as we do our lab for this week of class, we'll actually be able to try a whole bunch of these things that they're referencing in this chapter. So we'll get a chance to put some of this into use. All right. They remind us after installed, the cabling needs to be tested. Test for continuity and polarity. Also end-to-end insertion loss. How much attenuation or signal loss happens across there. With outside plant, they need to test and usually do an OTDR, optical time domain reflectometer. That's going to be distance and length and some potentially other tests in there as well, chromatic dispersion, spectral attenuation, those sorts of things that we'll talk about towards the end of the chapter. And it might need to actually test the power transmitter and receiver, power from the transmitter to the receiver, which would help with looking at attenuation as well. So a number of different tests need to be done. A number of fiber optic standards are out there for testing. Out of all those, the most important is insertion loss of installed fiber. That insertion loss, that's your signal loss. So you actually end up measuring power and then how much power is lost, if you will, to get your attenuation or insertion loss. So that's one of the most important tests to do. That's usually done with your optical loss test set that has the actual light source and then the meter, two pieces that plug onto the fiber run. And there are standards for that and which should be the minimum levels and so forth. They remind us cleaning connectors is super duper important. As we do our testing lab this week, most of the things we're going to test, we're going to clean the connector before we hook them into the tool or the meter and so forth. There is one time that I'll have you purposely touch your finger to the end and then see what it looks like under the microscope so we can see some of these things they're talking about. So they're reminding us to clean all the fiber connectors. Airborne dust can be as large as the core of the fiber. Dust particles can cause significant loss. Sometimes if the dirt is, I'm going to call it like sandy or something, it might actually scrape or damage the fiber. And oils from your finger can contaminate the connectors as well. If we take a look at, they had this picture in there showing you, here's a clean connector up here, dirty connector here, and after plugging them together a time or two, you can see literally the dirt and debris from this cable transfers to that port or that cable. And that's what they're showing you these over here. And they're showing you here some damage. If you were to zoom in, you could see some damage on there. The next couple slides, I have a couple pictures of close-ups to let you know. Here's what dirt looks like on the end of a connector under a microscope. Here's what oil or oily residue looks like under a microscope. Here's a smudge with your finger, so your fingertip oils, if you will. And then here is actually some scrapes and scratches across the end of the connector. That's what some of those things look like. We will see some of those up close and personal in the lab. So cleaning, we were using this in the lab. You can also use a lint-free wipe with some alcohol on. I'll be showing you that when we do terminations. That's one way to clean the end. And they do actually make these little pen cleaners. It actually, you kind of push in on it, and it actually does a little teeny swipe across the end of the port or the connector. I have one or two of those in the lab, so I'll be showing you those as well. And I just remind you, this is what a clean and polished connector looks like. All right, nice, clean, polished connector there. That's what we're aiming towards as best as we can. So one of the first tests they talk about is visual tracing. Visual tracing is just kind of that. I actually have a light source you can almost think of as like a flashlight that shines light into the end of a connector, and that'll allow you to see or have that light up on the other end to know that that is the connector or that is the cable. Now this is usually visible light, that it's not harmful to your eye. It's mainly there to light it up so you know that you have the right fiber. Maybe you have a polarity issue and you're trying to figure out which fiber is this really on the other end. Maybe a labeling issue for that matter too. Which fiber is this on the other end? So that allows you to visibly check that. Now, do remember, some of our visual traces do use a laser light source. So we have to make sure we're not staring at the end of the fiber. We need to look at that kind of off to the side at like an angle. So kind of imagine, holding a pencil in front of your face, but the pencil's pointing towards the wall, if you will. And you're going to tilt it just a little bit so you can see the end of the connector, but it's not pointing at you. That's the kind of looking we need to do. We do not want to point that light source towards our eye. The next type of tester, visual fault locator, we do have one of these in the lab room, and we will use this. The visual fault locator is going to use usually a red laser light source that is powerful enough that allow you to check continuity. So again, do I have the right fiber on the other end, or is it labeled incorrectly on the patch panel or something like that? This can trace fibers for a number of kilometers. This can help identify splices in a splice tray. This can even show breaks in the fiber or high loss connections or splices, if you will. As it shines through the fiber, it can literally just light up the fiber, if you will. If I take a look here, and they tell you down here, through most cable jackets, you'd be able to see that light. Through your outside, black cable jackets, that's not going to work. I won't be able to see it that way. But here is this is actually the type of visual fault locator we have. They're showing you going through a fiber, and that little red there is an actual break in the fiber and lighting it up. Here's another style, almost like a pen style, going through the fiber. You see some red there, but you really see it here. So there's definitely a break in the fiber there. Here's up close and personal. That's the kind we have, and again showing what a good fiber would look like. Here's one that has a break in, so it lets you know very quickly that's where the fault or the break is in the cable. There are sometimes, I think they even mentioned this in there as well, there's sometimes with terminating fiber or splicing fiber, you run the virtual fault locator through, and as you're mechanical splicing, that's the one I was trying to think of. When you bring those two fibers together to mechanically splice them, if light comes out the other end of the fiber, the one that that you're hooking into, then I know I have those mated well, and I can quick attach that mechanical fastener to hold the splice together. So sometimes you actually use these to see if you're getting as much of light possible from one fiber into the other one. I think they mentioned that in the book in your reading. Again, reminder about watching that light source. Make sure that's not aiming at your eye. You don't want to be looking directly into that. We're looking off to the side to see if there's light coming through. Next tester tool is our microscope. The fiber optic microscope allows us to look at the end of the fiber, the end of the connector, if you will, and inspect the ferrule and even the fiber itself in the connector. So you're looking for polishing issues, scrapes, scratches, chips, those sorts of things on the fiber that would affect light leaving that fiber and going into the next connector or the next fiber. So you're looking for, and these are some of the pictures they had for you. Here would be a good clean fiber. Outside around here is the ferrule. Here's the cladding, and then the center part there is the core. So that would be a nice, clean, polished connector. If I look at this one, I see a bunch of epoxy residue that's kind of squirted out of the end of the connector on top of the ferrule. And that could be affecting either the mating of the two, one connect to the other one, or light. It might be affecting the light moving from one fiber to the next one. This is a type of fiber optic microscope. I bring the cable into the end here, and this eyepiece up here is just what you would think a microscope. I can adjust the focus, and there usually is a light switch on the side to light the fiber either kind of like internally or light the ferrule, if you will. That's usually what that allows you to do. Make sure it's clean before you plug it in. Also, I'll remind you, I think I have it a little bit later here. I'll jump down right now. Reminder, we need to make sure we don't have that fiber connected to a light source. If you think about the light source going into it normally, going through a fiber microscope, it's now magnifying it 200 or 400 times going into your eye. So we need to make sure that's not connected to a light source before we hook up the microscope. All right, so as I look under the microscope, these are some of the common things I might see. This is what dirt ends up looking like on the end of the fiber. Here's what oily residue looks like on the end of a fiber, or end of the connector. Here's what maybe a smudge from your finger looks like. I'm actually going to have you purposely do that on one of the fibers so you can see it. And here's what a connector would look like with a bunch of scratches and scrapes across. And again, all these things are going to affect light moving from this fiber to the other connector or other fiber. They're going to distort the light moving through. This is going to refract the light and bend it out of the way and so forth. So all those things would affect the light moving from one fiber to the next. Here is this looks very similar to the fiber microscope we have in the lab room. Again, here you slide the fiber into this end. Here's a little compartment for batteries. And then here's your eyepiece that you can adjust the focus on. And there's a rocker switch on the bottom. Some fiber microscopes allow you to change the magnification. Ours has two different light settings. One, it lights the kind of fiber internally, if you will, and the other one that lights kind of from the side to see the ferrule. And as you look through there, you'll be able to inspect the ferrule more, or the core and cladding of the fiber more. The end of those usually unscrew that allow you to screw in different adapters to plug in different types of fiber, whether it be an SC, ST, or LC type fiber. This allows you to adjust that. Ours has, if I remember correctly, I think I have the wider one here to test SC and ST. That's the one I think I have in there, but I have the adapter to do LC as well. And again, here's our reminder about light, making sure that fiber is not connected up to a light source. All right, optical power. Moving on to optical power. Optical power is measured in decibels, and absolute optical power measurements. Actually, the actual power measurement is an absolute measurement, and the measurement of that is in decibels per milliwatt, if you will, dBm. Meanwhile, loss is a relative measurement, meaning we take a measurement of power through the cable and we look at how much weaker the power is on the other end, and from that you deduce how much loss there was. So this is a kind of like a strong power minus the power on the other end. That's how much loss we had. So that is a relative measurement, and the relative measurement for loss is usually just represented in decibels, and it's usually a negative, 0.3, negative 0.4, negative 0.5 kind of thing of loss, signal loss. Yeah, and this is what we say here, the difference in the power level before and after that component lets you know the optical loss. So as we do testing, and we'll do power and loss testing in the lab room, we'll hook up a known good cable and kind of zero out the meter, then hook in the cable we want to test, and we'll see how much signal loss has gone, how much the power has dropped as it gone through this new cable, and that'll allow us how much loss there is. Decibels is a logarithmic scale, so 10 decibels is basically a factor of 10, 20 decibels is a factor of 100, 30 decibels is a factor of 1,000. So it's going up, kind of like a big curve, almost exponentially, if you will. And if you do the negative, it's 1/10, 1/100th, and 1/1000th of the original power. And it's this right here. It's all referenced to 1 milliwatt. So they're basically saying a 1 milliwatt light source should equal basically a 0 level. So anything above or below that will let you know the gain or the loss in your signal. That's that angle right there, that line through the graph. Okay, calibration of fiber optic power measurements. All right, you typically need to calibrate your power measurement, your power meter, to a known good cable. We have a reference cable we use, and you would calibrate to the wavelengths of light you would be using. We're going to test in the 850 and 1300 range on our multimode fiber. That's what we're going to use. So we'll calibrate at those two wavelengths and zero it out before we start doing any testing. These meters calibrators do have an uncertainty, plus or minus 5%, if you will. So they are not spot on. There's a little bit of give and take, but any kind of measurement on loss or signal strength is better than no measurement. It gives us an idea or a ballpark we're working with. Periodically, the instrument should be recalibrated. That does cost money to send back to the manufacturer, if you will, to have it recalibrated. And they do say that it's not really, not as necessary maybe as other meters, but it is part of the process, if you will. All right, to measure, we need a power meter and a known good fiber cable, reference cable, if you will. And our fiber meter looks a little bit different than that. Ours looks more like this style here. Okay, this actually is the power meter itself, and this is the light source here. And then these would be your reference or test cables. Okay, we'll come back in the next podcast and keep on going.